Good morning. So we are going to conclude module 1 by today's lecture, and we are going to learn today an important topic, that is forced damped vibration due to rotating unbalance. Right. So we have seen in this series forced damped vibration. First, we have looked at forced damped vibration due to harmonic excitation of constant amplitude force. And then we looked at the force damped vibration for the base excitation. When the base is giving the displacement, harmonic displacement, then what would be the response? There we defined what is called displacement transmissibility. And the phase angle is slightly different than that of what we have looked at in case of only constant amplitude harmonic excitation case. So there are two cases so far we have seen, and today we are going to add with that forced damped vibration due to rotating unbalance. So I'm just going to share my screen and then go ahead with our class. So am I, is the screen visible to you? Is my board visible to you? Yeah.
Yeah. Yes, sir.
Yeah. So this is lecture number 11, and today it is 27/08/2021. So what is that? Today's class we are going to see is damped force vibration. Due to rotating unbalance. This is the topic. When you see this, so we know that many of the machineries, though they are balanced for its static balancing, especially the rotating machineries like turbines or an electric motors or compressors, for any rotating machineries that are balanced, even though they are balanced, there can be some kind of an unbalance, eccentric mass that can be present in the rotating element, and that would cause a disturbance or an excitation to the system, and that can be mathematically modeled as damped forced vibration. So the damped word is because you know that if it is undamped system, the excitation frequency happens to match with the natural frequency of the system. You would expect an infinity amplitude hike. So there can be breakage of the system or malfunctioning of the system. So that is why damping is very much essential, that though you are aware that your operating speed is much far away from that of the natural frequency of the system, but you have to cross that to go to that highest frequency of excitation. So the damping is inevitable in such system, any rotating machinery. So with that note, let's just start today's class stating this. And example, let us look at an electric motor has got an eccentric mass, and that is undergoing forced damped vibration. Right. So I will put that schematically, motor and its rotor and its base. Is attached to a spring and a damper, and then it is grounded. So now let's look at the total mass of this motor is m, small m, and you have an eccentric mass. Maybe this is my reference axis, and I have this is rotating element. So this is rotating with the speed omega, constant speed omega, and I have here an eccentric mass, say m naught. That is m naught. The m naught is smaller than that of this m, and this is placed radially at a distance e. And as this is rotating, what will happen? There is a mass concentration at this point. That's what is m naught. M naught is inclusive of this total mass. So the total mass of the system, if we take this m naught, is inclusive in this. But let us consider like that. So this would create a centrifugal force, and that would be given by m naught e omega square. That you know, right? How does it come? So this is centrifugal force. So this force, vertical component, would always create. So any instant of time, its angular position is given by omega t. Let's consider. From the reference axis, omega t is this centrifugal force is acting. And because of that, what will happen? It will excite vibration, and that vibration is what is forced vibration now. And since there is a damping element in this model, so the system is sufficiently damped. So this is damped forced vibration case. And of course, you know, damped case means it's under damped system, then only you will have a oscillation. If it is critically damped or over damped system, they are aperiodic and they will have special purpose in system when you want to prevent vibration altogether. So you do not want any oscillation, then only your damping would be either critical damping value or that's more than the damping ratio, right? So that we have already seen, you are very much aware of it. So this would undergo now a vibration from its mean position. Always you see that word static equilibrium position. That's important. So with that x of t is what is its response. So this is how we are now modeling our study. So if that is so, I can get my governing equation now by applying Newton's law. And let me write that now here. So m minus m naught, because I take now this mass except this unbalance or an eccentric mass, right? So this m minus m naught into d squared x by dt square plus I'll take this m naught, so m naught into d by dt square, d square by dt square of, see now this m naught is positioned where from this point reference at the distance a. So you have here already this x. So this mass would be projected on this, will have already x plus this e. So you would have here, this is going to go m naught from here x plus e. So x plus e sine omega t is what is this. So here x is varying and e sine omega t is what is this projection distance where this m is located. So I should differentiate this like this. So this is what is from mass, and this what is going to be equal to, when I draw the free body diagram, I will have upward positive. So this is positive. Downward the forces are spring force, that's minus k x minus c x dot, damping force. So this is what is application of Newton's second law to get the governing equation for this case. So now let me just expand this. M into d squared x by dt squared is x double dot minus m into m naught into x double dot plus m naught into x double dot plus m naught e into c d squared by dt squared of sine omega t. So omega is, again this omega t function is there here. So you would have this is going to be differentiated twice. So what is that you are going to have here? This is going to be just a minute. Let me have it like that only, d squared by dt squared into e sine omega t. That's equal to minus kx minus cx dot. So this goes off, and I have now my terms mx double dot, and let me have my cx dot, which is on the right hand side to this left, plus cx dot plus kx, and this would be now going on the other side. And here, what is this second derivative of this is going to be cos, and then sine, there is a minus term. So that's going to be m naught e, that's omega squared, because 2 times you are differentiating this into sine omega t. So this is the governing equation now. This is the governing equation. So this governing equation, if you look at, it's very interesting. It is very comfortably, you can handle this. And I would call this portion the coefficient of this harmonic function. So this portion by f naught. If I call this as f naught, I am done with my studies. So like the case 1 where we have looked at f naught sine omega t. So how does it come? The same way the response will come. The only difference here is this f naught here is not constant. If I vary the speed of this motor, you see this value is going to vary. But in the first case, we have taken f naught sine omega t, where f naught value was constant amplitude we have taken. But now this is like in the case of 1, it is not independent of excitation frequency. It depends on the excitation frequency. So what is that speed it is given here? That's going to dictate. In case if I vary this omega, instead of running it at constant speed, what would happen is this would be varying. Obviously, that would have an effect on our displacement transmissibility that we have seen. So similarly, magnification factor we have seen. So you would have the effect of those characteristics as that is function of omega. So we had an x-axis r. R is omega by omega n. So if you vary omega, what would happen? We study. So if you vary this omega, this f naught value is going to vary. So your response curve, what we had looked at, will not be same in this case. That is what we will be seeing it now. So let's now get what is the response for this. So the response to get, you have the same procedure, have a trial solution, substitute in this, and then you will have complementary part and particular integral part. So the complementary part is transient, that would be similar to that of first case, so that would die out, and particular integral part response would be in this form. So I'm going to write only the response now for your understanding. So the response would be x of t is going to be, this is what response? Steady state response. Steady state response for this would be x of t equals amplitude times sine omega t minus 5. So when you put this, it's very simple to remember these equations when you draw the vector diagram. So I'm just going to draw the vector diagram for your benefit. So let's have a reference here. This is my reference axis. So let me place first my vector, which is my f naught vector. So that f naught vector is, say, this is f naught vector, m omega squared e, right? And the displacement vector, that is my response, that would always lag this excitation in force response study that we have already seen. So that vector, say, this is. So this vector initially at what orientation at any point of time, it's at omega time. So the angular position is omega t for this. And for this response x, that lags this by phi angle. See nicely that vector represents. So now because of this x displacement vector is there, you would have your spring force. So let me just take that here. That is kx. And I would have my force due to damping as the velocity vector leads 90 degrees in simple harmonic motion that we have seen. This would be c omega x here. This is capital X. And then I would have my inertia vector 180 degrees out of phase to this, or that leads, acceleration leads the displacement by 180 degrees that you know. So this comes here, m omega squared x. So like that it comes. So in this vector diagram, you are now able to write what is your amplitude in this response. That will be simply given by this. So I'm just going to take here. What is this m omega squared e, right? So that's what x is equal to m naught. This is m naught. I'm sorry, this is not m naught e omega square. Like f naught by I write, right? So f naught by this, when I write, what is this? You can just draw this line. So it is 90 degrees here. So I would have this denominator. That's going to be kx minus m omega squared x. And that x is what is taken here. So that's going to be k minus m omega square whole square plus c omega square. Right? So this is what is my x. So you see from this vector diagram itself, what is this length of the vector m naught omega square e? And that would be equal to this side square plus this side square. So what is this side square? Kx minus m omega squared x whole square. So that x is what is there is taken out, and that is taken on this side. And that is how you get this expression now, which is your dynamic displacement amplitude. And this can be now, I can rework on that, multiply this by mass, divide by mass. And then I can rewrite this as m naught e by m. And m omega squared e. Sorry, e is already taken here, so it's not the m omega squared divided by under root of k minus m omega squared whole square plus c omega whole square. So this is going to be further. This is going to be further. Like I had in the first case, f naught by x is what is static displacement that is brought down here to define magnification factor. Now this term I'm going to bring it down. So this is going to be x by m naught e by m. And on the other side, this is going to be m omega squared. If I take k out here, what will happen? M by k will be there. And I will have inside this. So that's going to be m by k into omega square divided by, here it is going to be under root of 1 minus m omega square by k whole square plus c omega by k whole square. So this is going to give you a very interesting form that already we have seen, we are familiar with. And I'm going to rewrite this as k by m is omega square, omega n square, natural frequency square. So omega by omega n whole square in numerator. And in denominator, it's going to be 1 minus. So this term is again omega by omega n square. And this all whole square plus c omega by k, we know that it is 2 zeta omega by omega n and square. So this is inside this radical. So this is going to be x by m naught e by m. So look at this now. So nice it is. This is what is that ratio here. Your displacement transmissibility ratio, like that. So this mass goes, this is displacement, this E is again radial distance E. So this ratio is now given by this. Like magnification factor of case 1, now you have, this is the magnification factor for damped force vibration due to rotating unbalance present in the system. So you may ask a question here. So when we draw this free body diagram, we have taken only this vertical component. What about the horizontal component? So horizontal component is neglected, or it is constrained to have only vertical vibration. So the horizontal component, why can be neglected is because This is erected on a foundation of huge mass. So that is what you should see, engine bed in our laboratory or anywhere you go. And that is not just being kept on a floor. So that is mean that the entire engine bed or any motors are kept on a big rigid foundation. So that to take care of increasing the stiffness as that entire system masses increases with the foundation. And you see there will be horizontal stability maintained, and you can neglect that. It would have only vertical vibration, right? So it is only one motor, or you will have an arrangement like you have another motor rotating in this sense, then they are coupled, then you see that will be cancelling. So like that, the thing will be there. The vibration is only one direction. So in this case, it is in one direction. This component would be constrained and then that is neglected, or that is balanced by the support, and the vibration is only in vertical direction. So that you should be remembering. Again here, what is that another interesting thing that we require? Look at, I have now my amplitude. So the amplitude is now in my response, steady state response is x equals this entire expression multiplied by this factor, m naught E by m. That is my amplitude. So what is my phase angle? So the phase angle will be tan inverse of, look at here, this is that. So opposite side is c omega x by adjacent side kx minus m omega squared x. So this x goes off. So I would have c omega by tan inverse of c omega by k minus m omega square is what is the phase angle. So what does this phase angle represent? Here the disturbing force, an unbalanced force, that is centripetal force, leads this response of your damped force response by phi angle, or this lags this excitation by phi angle. So that is how you should say this phi. So now if you have understood this, traditionally what we were doing for the first two cases, we will look at now how this x by m naught E by m varies as function of r, where r you know is frequency ratio omega by omega m, right? So if that is so, let me take now vertical axis. In this I am going to have x by m naught E by m, and horizontal axis I'm going to take r. So r can be 1 to represent an resonance state, 2, 3 and so on. So now you look at here, in numerator in this equation I have omega by omega n whole square. So when omega is 0, I will have this transmissibility is 0. So it starts from 0, unlike in the previous case. So it starts from 0, and I know this is very interesting point. When omega is equal to omega n, that is going to be the resonance state of your system. So this response would go like this. And in the other cases, you have seen that beyond this r is equal to 1, greater than 1, or greater than 1, they all had come to 0, but now it is going to be, interestingly, it's going to be 1. So when you see that omega is much greater than omega n, that is r tends to infinity, this value would tends to 1. So your response here tends to 1 asymptotically. So this is when zeta value is 0. So it is going to be infinity. So when you have a zeta value, what will happen? Your graphs would be, look at again here, very interesting fact. It would be skewed not to the left like in the first case, slightly to the right it is in this case. And this is again going to approach 1. And then as you increase the damping, you see at the resonant point, you have your peak broads down, amplitude broads down. So if this is zeta equals 0.125 and this zeta equals 0.5, so maybe I would have one more curve here, that is zeta value is 0.25 and so on, And you see now again at a value when zeta value is 0.707, after that you do not have a peak, and you would see that it goes all to 1. So this is 1, 2, 3, and so on. So these all are aperiodic, and you have only this. So this is what is going to be your characteristic variation of this as function of R. And your phase angle, if you look at, there is no change from that of the first case. So the same expression you have. So you would have at resonance, irrespective of damping, you would have it is 90-degree phase angle. And 180 degrees phase angle would be reached asymptotically. If it is undamped system, you would have only two states, in phase or out of phase. So R value less than 1, you would have it is in phase. R value greater than 1, you will have out of phase for an undamped system. So this is for zeta equals 0. If zeta value is start coming, then you would have this all going through this. Like this. So like in the first case. All approaching asymptotically to 180 degrees. So this is what is the characteristic of your magnification factor, analogous way to say to that of frequency ratio, and the phase angle variation as function of R for a damped forced vibration due to rotating unbalance. So do you have any doubt? I would be clarifying this doubt. If you do not have, let's proceed further to see many more interesting aspects of forced response study. So here some of the conclusions are critically to say that when you look at, I just to put that here. Like you have here 3 cases. One is, see here you have this value all starts from 0 instead of 1. That's one thing. And then how do you say then when omega is very, very less than omega n, that omega tends to 0, not omega, yeah, omega tends to 0, you see that this x by m naught e by m is equal to 1. Sorry, is 0, tending to 0. And when omega value is much, much greater than omega n, and you see this x by m naught e by m tends to 1 unity. So that's first understanding here. And what is the value at omega? At omega is equal to omega n, you would have your value x by m naught e by m would be equal to 1 by 2 zeta. 1 by 2 zeta. So like we have discussed in the previous case 1, we can also have the discussion between zeta value between this to 1 by root 2, because there is to see this 0.707 only peak is there. After that there is no peak. After that there is no peak. So you see in this what is the maximum value of this? So this is not maximum. So this is at omega is equal to omega n. You want to see this, what is the maximum value of this? You know this ratio is function of omega by omega n. So this function m naught e by m, to get this maximum value, what you have to do is you have to differentiate this by r, x by m naught e by m, and equating to 0. That would interestingly give you when r equals 1 by minus 1 minus 2 zeta square. So whereas in case 1, this value of r, when you do this in differentiation, was simply r is equal to root of 1 minus 2 zeta square, where that value is always less than 1. So these peaks are skewed to the left on this side. But now since this ratio for this, when you solve, you get r value, because the solution of this is what it's a polynomial equation you get, and that r you would have an algebraic form when you differentiate. So that's how you get this r value. So the r value here is, since in this case is this, you get this peak is on to the right. So this much of clarity of understanding is important for this case. So that is the difference between case 1 and case 2. Case 1 is what? F naught is constant. This constant is what is case 1. What we have already seen. Case 2 is what is this current one. Let us call this case 3. Case 2 is base excitation we have studied. Case 3 is what is current. Current one. So here F naught is not constant. F naught is directly proportional to omega square. That's why you see this term. This is going to be this, and the peak here is skewed slightly to the right. So the maximum value you will get here by substituting this. So when I substitute this maximum value, what is that I'll get? This similar to the case 1, and that value would be this x by m naught e by m, max value would be 1 by 2 zeta into 1 minus 2 zeta square. So this is that maximum value, and that would be slightly to the right of this point 1. If you have understood that, then any value, this is 5th point, any value of zeta greater than 1 by root 2, if we take, there is no maxima time. So the x by m naught e by m does not attain maximum value, right? And we know that that all going to be equal to 1 at r tends to infinity. At r tends to infinity, this is going to be 1 value. So that's what we have been observing from this. So now, what is the other interesting point here is what is called, okay, we will stop at this point, this case. I'm going to now look at what we were doing in the last class once again, right? So what is that?
Excuse me, sir.
Yeah.
Sir, what is written in this last line? After x by m not e by m. Yes, sir.
Where? Which point you're asking?
Sir.
Does not attain maximum value. So when zeta value is greater than this, that is 0.707 here, right? You see there is no maxima, it goes gradually to this. So there is no peak comes, and that is what is I just have written. And as r tends to infinity, that means omega is much greater than omega in this case. You see this, what is this value? This tends to, this is this again, x by m naught e by m tends to 1. So that's what I was writing. Is that clear? Do you follow? Is that your doubt?
Excuse me, sir.
Yeah.
Can you tell again at what condition is x by m naught e by m maximum 1 by 2 zeta into root over 1 minus 2 zeta square?
How do we get this? That's what is your question, right?
No, sir. At what condition do we get that?
What condition do you get this? When you have your excitation frequency, right? Your excitation frequency is closer to that of resonant, but not at resonant state. See, that's what is this point. It is not, these peaks are not at the resonant point. It is slightly adjacent to the resonant point.
Yes.
Right?
Yes, sir.
So if you have like this, so your natural frequency and this is very close. So you have studied something in free vibration called a beat phenomena. That would come here. That will be beating forcefully the system. and beating forcefully the system would have the amplitude goes to maximum and comes, same kind of thing would be there. But you are not going to operate any of the system at these points, right? At these points. So these are all the inference what would happen to your system in case of your excitation speed, or in case you run your motor in this case with this unbalance with that omega value, right? So what is that omega value? With that omega value, when I say what is that omega value, omega by omega n is equal to this. Omega by omega n is equal to this, right? So what is R here? That's equal to omega by omega n. So when I say omega is equal to omega n divided by this, I would have one frequency, and that frequency is greater than omega n, because zeta value is such that you would have here this value is greater than 1. So, and that is closer to the closer to this resonance state, and that would be the peak value. So how do you get this? When you have this function, what is that function is this? Look at this equation. Look at this equation. So this equation, you are differentiating this with respect to omega by omega n. In the first case, this was not there in numerator, but now it is there. So when you differentiate that and equate to 0, you get a value of omega by omega n. And that value, you get this maximum value. So I have skipped that part. That's not needed. You know what is that mathematics behind. We have done for first case. Similarly, you can carry out. For the time limitation reason, I am not doing that. You can do that exercise. So now when you differentiate this equating to 0, I get R value this. So I just write here what did we get, or I will show that what we have got in our first case. So this is not the first case, right? This last class we have seen. Let me open the previous class lecture. See here we were doing that, right? See here, you see these peaks here is all what is skewed to the left of 1, R is equal to 1. And we have got this. So we were magnification factor, we are differentiating with respect to this, equating to 0, we have got here. Look at now what is that I get here, omega by omega n, I get this. When I differentiate this equating to 0, I get my omega by omega n value is this. But now what is that I have got it in this case? In this case is today's class case. I get, instead of that R is equal to root of 1 minus zeta 2 zeta square, I will get 1 by that reciprocal I get it. So if that is reciprocal, my omega p would be omega n into divided by this. So you would have this question in your competitive examination. So you have to look at that when you got damped forced vibration due to constant amplitude harmonic excitation. Omega p is what? Omega n into under root of 1 minus 2 zeta square. If the same question is asked, what is your peak amplitude in a case of forced damped vibration of the system due to rotating unbalance, then the same should be divided. See, so carefully you need to understand and remember things. Right? Are you getting my point? Yeah.
Yes,
so,
sir.
yeah. And similar way, how did we substitute here and we got back this maximum value? If you substitute that, you get the same maximum value here as well. So when you put this omega p by omega in this back, and you will get this. And that will not change. That is same. Only it is skewed to right or left. So it is you are being required to test your mechanical vibration fundamentals, and the interviewer is strong in vibration, you would ask such things. So you would be impressed if you are saying this all so clearly, and you would certainly ask who has taught you this course, right? So with that, let's proceed. So there are some more interesting things to see. Another 10 minutes we will end the class. And what is that I'm going to introduce is, now you have understood what you called displacement transmissibility. Case 2 you have seen, right? And now what is force transmissibility? Let us understand. So for that I'm going to take this. So before that, let's just look at what we did in the last class. We had mass and spring damper system and a base plate. And this base plate was given excitation y of t equals y sine omega t. And this was going with the x of t, right? So the base was vibrating. So this can be like a vehicle going on a road profile in a test track for its endurance test, right? So then there will be a response here, and that response is what we have looked at in the last class as this. What was it? It was mx double dot plus c into x dot minus y dot plus k into x minus y, that's all equal to 0 when I apply Newton's law, right? So I get this. So now in this, I have taken this y part on the other side. We did all those on the last class. But what did we do in the last class is to look at what is that displacement transmissibility. How is it defined? Absolute dynamic displacement to that of base excitation amplitude. That is what is there we define. So let's just look at what we did in the last class. So see here, we were doing this derivation. We are doing this derivation, right? And we were bringing this on this side, and we have used our known trigonometry. This vector diagram was wonderfully made you to understand. And then you had this x by y finally, what is called displacement transmissibility, you define. So this displacement transmissibility, you had this expression now you see. So for this expression, how this would vary, this displacement transmissibility would vary as function of r is what we have seen. And the main difference here is the base excitation when it comes, this x would be lagging to that of y by phi minus alpha. That is the phase angle here. So far we have looked at only phi, but in this case, it is phi minus alpha. So you have to take this always as a phase difference of x to that of y. And this ratio is what is defining displacement transmissibility, right? So why did I show this is that you will understand now what we discussed today, right? So here I'm just going to look at, instead of what we have seen here is what is an absolute motion. Absolute motion. Absolute motion means what? Here I look at what is x of t. I'm not looking at what is x of t as with reference to y of t. So this is also vibrating, base also is vibrating. Our base is what is making this to vibrate. And they can go with the vibration or out of vibration. That's different. So that is all depends upon your system nature. So now this absolute motion, what we have seen, can be looked at instead a relative motion of mass with respect to base, because both are moving. So then what is required? Relative motion. So let us look at how do you look at this response with reference to base motion, right? So that is what I am going to explain you now. So mx double dot plus c, this is there. So I am going to define now my z is equal to x minus y. So what is z? Is mass displacement with respect to base. That is z. That is x minus y. You know that, right? How does it come? And let relative displacement amplitude or relative displacement, if I put, it's not amplitude, it's z of t, x of t minus y of t, like that you can say, is this, then what is that? I'm going to have it here is mx double dot plus cx dot minus y dot. Instead I'll write cz dot plus kz, that's equal to 0. And I can rewrite from this x is equal to z plus y. So let me put that here, m z double dot plus m y double dot plus c z dot plus k z equals 0. So I'll rewrite this expression m z double dot plus c z dot plus k z. So you see on the one side it is relative displacement of mass with respect to base, and then you get your excitation coming from m y double dot. minus m by n. Yeah. Any doubt?
Oh,
Huh? Any
Sir, can you
doubt?
no, sir.
Someone is asking. So if you do not have doubt, I will proceed. If you have doubt, I will explain. But if you disturb now, if you do not follow, later on we will discuss after the class. Let me finish it. Right. So now this is equal to my double dot. So you can rewrite this now. Y double dot. What is y? By the way, y sine omega t. Y of t is equal to y sine omega t. So y double dot is going to be y omega squared sine omega t minus y omega squared. That minus of minus become plus. So minus of minus become plus m omega squared y sine omega t is what is m z double dot plus c z dot plus k z. So now you know why do I do this all. So look at this, the coefficient of sine omega t. That's something similar to what is my f naught. That's something similar to what is my f naught. So my steady state response z of t would be now what? Z sine omega t minus phi. Omega t minus phi. And amplitude, this z amplitude would be equal to m omega squared y by under root of k minus m omega squared whole square plus c omega whole square. Right? And phi would be tan inverse of c omega by k minus m omega square. So this is similar. Why? Because f naught sine omega t I have it. So this is like a case 1. So I will have my amplitude like this here. So you want, you can draw the vector diagram. I'm not drawing. You can draw the vector diagram and understand this. So you don't need to struggle to remember this. When you draw the vector diagram, you can easily write this equation. That's what I've been explaining you. So now this is your amplitude and this is this. So in this, now I'm going to slightly do some manipulation to get it in a neat form. What is that manipulation? Is this. Yeah. So what you do here, you take this k out from here. From this, if you take k out, k by m is equal to omega n squared. So this, you can bring it on that side. That's going to be z by y equals here omega by omega n whole square divided by under root of 1 minus omega by omega n whole square plus whole square. This plus 2 zeta omega by omega n whole square. So look at now this, what do I have is similar to what we discussed in the previous section. What we have is what we discussed here. What we discussed for rotating unbalance, right? What we discussed here for rotating unbalance. So I can have the same graph for z by y as well. Z by y as well. And phase is same. So what is that equivalence? Damped force, sorry. Damped forced vibration due to rotating unbalance is same as that of relative motion of mass due to base excitation, right? Absolute motion, if you look at, that is different. Absolute motion, if you look at, that's different. So if you have understood this, we have one more point to complete today's class. What is that? Is force transmissibility. Excuse me. See this force transmissibility. So how do you get your force transmissibility now? This is what we will see. Displacement transmissibility, you understood, right? So what are displacement transmissibility? It is x by y in case of absolute motion of mass to that of a base excitation, or it is z by y in case of relative motion of mass to that of base excitation. Also equivalence magnification factor or the other rotating unbalance. So 4 cases that we have seen. So now let's define what is force transmissibility. Force transmissibility is defined as force transmitted to the base. See, you have a huge machine which is running. You stand nearby the floor. You feel some kind of vibration in the floor. Why is it? Because that rotating element of the turbine in a power plant is what is causing the energy to come to the floor ground. So you may have some ground vibration. So if you have a huge machinery in the first floor, you may feel there is a vibration on the ceiling or comes down that get transferred. So that is what is called expressed through force transmissibility. So how do you define force transmissibility? It is force transmitted to the base. Force transmitted to the base to that of an impressed force or excitation force. Impressed force. So how do I look at it now? I have my mass. Instead of hanging it from ceiling, I do have it now in this way. And instead of having base exciting, base fixed. So if this is the undergoing now with the force excitation, F of t is equal to F naught sine omega t. And you would have this vibration x from its static equilibrium position. So I would have the corresponding governing equation. You know that it is the mx double dot plus cx dot plus kx equals f of t. And you know x is equal to f naught by k by under root of 1 minus r squared whole square plus 2 zeta r square. This is all you know. 2 zeta r whole square. So now, what is force transmitted is FTR, that is going to be, these two elements are attached to this. So what is the reaction that comes from these spring force and damping force is what is your force transmitted to the floor. And that FTR is going to be given by this. So let's look at the vector diagram. It's very interesting to understand. So you have at any time your impressed force amplitude F naught, that is excitation force, impressed force I say, the word I say, and that is placed at omega t because it's F naught sine omega t now, and you have your displacement lags by phi angle, and you can have, because of this, the spring force would be kx, and then your damping force at 90 degrees here, c omega x, and then your inertia force m omega square x. Is this diagram. What is transmitted force here is this. Force transmitted is this. So this difference here would be phi minus. So this angle here is what is phi minus alpha. So you see here this angle, impressed force angle is alpha. So this angle is phi. So this angle is phi minus alpha. This angle is phi minus alpha. And this is FTR and this is F, right? So it appears this length can be smaller. So it can be greater than F naught or less than F naught. If it's greater than F naught, that means it is amplifying the force. That's not preferred. If transmitted force is less than this, it is better. So the transmissibility function to draw, I just have drawn the vector diagram. This is for an instant omega t. So this would vary, this all, right? You know that. So FTR here is now the resultant of these two. So that's going to be x into under root of this square plus this square. The x is taken out, so it's going to be k plus c omega, k square plus c omega square. So I'm just going to take this from here. I'm going to substitute here what is x. This x I'm going to substitute here. So that's going to be f naught by k into k square plus c omega whole square divided by under root 1 minus r square whole square plus 2 zeta r whole square. And you see now here this k goes inside. That's going to be f naught into 1 plus c omega by k, that's going to be 2 zeta r whole square divided by the root of 1 minus r squared whole square plus 2 zeta r whole square is what is FTR. So now what is my definition of force transmissibility? F, that's going to be FTR by F naught. So this is here FTR by F naught is what is defining force transmissibility. So that this will be brought down. So I will have a numerator 1 plus 2 zeta r whole square divided by under root of 1 minus r square whole square plus 2 zeta r whole square. So look at here, force transmissibility is defined like that, and you get this similar to that of what you have seen in the second case. Excitation, absolute motion is similar to that of absolute motion of mass to the base excitation, whatever response that he had. What was that? X by y. X by y, what he had is similarly what we have here. So that was FD, and now force transmissibility is given by this. And of course, this angle phi minus alpha. Yeah.
So in the denominator,
yeah,
f naught is 2 zeta r the whole square, right? That's 2, right?
2 zeta r whole square.
Okay.
2 zeta r square. All the time, see this, you will always see this term, once you rewrite, and that's why you are making notes, you will become familiar with that. So the r is omega by omega n, right?
Yes, sir.
Yeah. So this is here again 2 zeta r by 1 minus r square minus tan inverse of 2 zeta r. So you see in some textbook this is combined again, and then you have written. But no need of combining and struggling to remember that formula. You can just always remember this. And this is all easier when you draw the vector diagram. That's why I started vector representation of simple harmonic motion in the very first class. So with this, I would stop today's class, and this completes the basics of mechanical vibrations. If you have any doubt, I can. So how many different cases that we have done? Can anyone answer that? I would be feeling very happy. What are the 4 different cases that we have seen in damped forced response study? Anybody? One who asked doubt. Right or wrong, no matter. You please tell, then it is easier. Or I will summarize now. So there are 4 cases. The very first case is this, what we have seen. Just we have it here. That is excitation due to constant amplitude f naught cos omega t. That's what we have done, where we defined what is magnification factor. And you see this magnification factor as function of r. How does it vary? Also, it is varying as function of zeta. So you are having 3 different zones. At the resonance state, that zone is called, vicinity is called damping controlled zone. Anything less than r value 1, r value between 0 to 1, here what is this zone is called? Mass controlled zone, sorry, stiffness controlled zone. And the one which is at the value omega much greater than omega n, that's called the mass controlled zone in all the cases. So, and the phase angle difference that you have seen. So here we have done very detailed study on the very first case, where we had a constant amplitude harmonic force excitation and its force response. Then we had looked at this base excitation. So when I have my vibratory system, because of excitation comes from base y sine omega t. If I have to get my response, steady state response, which is the absolute motion of my mass alone, if I have to look at, then I had got my equations here like this, and the phase angle is now more only phi, it's phi minus alpha, to say what is that x lags y. Y is what is impressed displacement, x is what is the response. So they have a phase difference phi minus alpha. So this is what you have seen here, and see here, interestingly, you have this expression, right? And now, and you also have looked at this in this case. So you know why this is skewed to left and right in the next case all. And today's class we have looked at the third case. What was that is rotating unbalance. So damped force vibration due to rotating unbalance. So when you see this, you have your response, and this response amplitude is going to be now case 1 multiplied by omega and square term is coming. This is new additionally coming. And because of that, you see that response characteristic, instead of starting from 1 in the first case, and second case starts from 0, and there they are all converging to 0, but this all goes to 1. And then your phase is going to be same. There is no difference. And after this, the fourth case, what we have seen is looking at the base excitation, and there is motion of this mass instead of absolute motion relative to this base. If you look at, you see interestingly that again falls in this category of rotating unbalanced case expression. That is why we had this graph here. Additionally, we were able to put this term also here. So z by y also would be varying like this. And then the fourth case was force transmissibility. So when you have to understand the force transmissibility, I have taken now the first case and then I have explained. So for every case, you can look at what would be the force transmissibility. So accordingly, you would have your response comes here, right? With that note, I'll stop this, and this ends module 1 and basics of mechanical vibration confining to single degree freedom system. We have only one mass. So the entire passenger car can be considered as one mass, and that is seating or interacting with the road surface because of equivalent spring and damper coefficient or the values of the suspension system and tire. If you put all of them, you can very well do single degree freedom vertical vibration study to account what is this happening. So this can further help you to understand what you mean by isolation. Is that vibration response is isolated? So you see the interesting part of your vehicle design, the unsprung mass. So unsprung mass is something designed and attached to the sprung mass, which is the mass of the vehicle above the suspension, and the system become convenient to isolate most of the energy that enters the vehicle. So this all we will see again in vehicle dynamics. So when I explained their 2-degree freedom system called quarter car model or pitch and bounce model, you would comfortably able to follow what am I doing, because you have learned fundamentals of mechanical vibrations, right? So if you do not have any doubt, I would stop at this point of time the lecture. Any doubt? So if you